So this is the next chapter that we're going to do after the bonding chapter. So this is called kinetics. And like it says, kinetics is a branch of chemistry that deals with the rates of reactions. Now, before we talk about the rates of reactions, we have to go back to the bonding chapter. And when I told you that in order to make a bond, when you make a bond, energy is released, okay? And if you want to break the bond, you got to put energy in to break the bond, okay? But before you make the bond, when two particles collide, that's exactly what you have to have. You have to have a collision between two or more particles. And not all collisions result in forming new compounds. So, the first thing we're going to do is talk about the collision theory. I have two molecules of HI, all right? Now, you can't just collide any old way and think you're going to have a chemical reaction. So the first thing is this. If they go past each other, that's not proper orientation. And if they hit this way, that's not proper orientation. They have to hit a precise way. So if these two molecules are coming toward each other, they would have to hit just like this. So the very first thing under the collision theory is the two particles must have proper orientation. Proper orientation. All right, that means they must hit at precisely the right part of each molecule or atom. Now, the other thing is this. The big deal is they not only have to hit precisely, they have to have enough energy to do something. So what do they have to do? Before forming new bonds, they have to break the old bonds. So if they have proper orientation and they just glance off each other, that's not going to break this HI bond here and the HI bond here. So the other thing that two particles need, they not only need proper orientation, they have to have enough energy when they smash together to break the old bonds. And this energy has a name. And the name of the energy that's used to break the old bonds is called activation energy. So, there are two things you need. You need proper orientation of the two particles that are going to collide and enough activation energy so when they do collide, they break the old bonds and then new bonds can form. Okay? All right. Now, I like to use this analogy. Matchbook Match. These are two particles. They're going to collide. But if they go like this, they didn't have proper orientation. If they hit here, not proper orientation. But if the match hits the rough area of the matchbook, that's proper orientation. But watch. What's missing? Nothing happened. All right? So you need two things. You need proper orientation and enough activation energy to start the reaction and break the old bonds. So what we're going to do is we're going to make a graph using these two particles, okay? First of all, we know that both of these particles, as they're whizzing toward each other, they both have potential energy to do something. So let's build a graph. And on the y-axis, we're going to say that's the potential energy, PE. And we're going to go up to like this, 10, 20, 30, 40, 50, 60, 70, 80, 90. And potential energy will be expressed in kilojoules, which is kJ. All right, this is just the reaction coordinate, or like I tell the kids, time for the reaction coordinate. Now, let's just say that this match and this, they have this much potential energy. Let's say they have 60. All right, 60 kilojoules of potential energy in these particles. So we're going to call this the reactant. So these are the two reactants. Now, what we have to do is, first of all, remember, for a collision, we have to break the old bonds, and then the new bonds can form, giving off energy. But first, we have to break the old bonds by putting in some energy. So, watch. Remember, this is not proper orientation. This is not proper orientation. This is proper orientation, but there wasn't enough energy to break the old bonds. So now, they're whizzing toward each other, and all of a sudden they hit. There's enough activation energy to break the old bonds in the match, and now new bonds are being formed. And as you see, as the new bonds are being formed, energy is being given off or liberated. Okay, now let's put that in the graph. So if we look, this is the reactant that we started out with, and this is the product that we ended up with. Okay? This has more potential energy than this, because the potential energy in that match turned into kinetic energy, and so there's less potential energy there. So let's just say that the potential energy of the product is down here at 20. We're going to label that P. Now, the deal is, how did we go from the potential energy of 60 down to the potential energy of 20? Did it go like this? Did it go straight down like that? No, it did not. Because remember, we had to break the old bonds before you had to form the new ones. So it did not do that. We had to put energy in. And remember, that energy is called activation energy. So I'm going to erase this part. And we put energy in by striking the match. So here's what happens. We go up. We went up to 80, let's say, and then we came down. Now, remember, reactant, it was these two. And when they were coming toward each other, remember, with speed, they're coming toward each other. That's going up this hill. Up, 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 up. And finally, when they smash into each other, the old bonds are broken and the new bonds are formed. Okay? So this energy right here is called activation energy, and that's where the match strikes the matchbook. And then old bonds are broken in the match, and this energy is given off. Now, how come the products are not all the way down to zero? Because if you look at the match, it's not burned all the way down to the end. There's still some potential energy left in that match. So what we're going to do is this. You have to say to yourself, did I have to put more energy in, this reaction, or did I get more energy out? Well, you struck the match, and when you struck it, you put activation energy in, but when the old bonds broke, the new bonds formed and gave off a lot of energy. So in this particular case, you got out more energy than you put in. And if you get out more energy than you put in, you can say that the energy exited, or that this reaction is an exothermic reaction. Exothermic means you got out more energy than you put in. And the equation for an exothermic reaction is this. A plus B yields C plus energy. A and B, oh, if you want, that was the match in the matchbook. And when you struck them together, you produced C, which was a burnt match and a lot of energy. So when you see the energy on the product side, that means you got more energy out. That is an exothermic reaction. Now, what we're going to do is we're going to go over all the line segments in this graph. And hopefully you'll understand. It's kind of easy. Before we put line segments on this graph, I want to make some dotted lines. I want to make a dotted line where the reactants are, a dotted line where the products are, and a dotted line at the very top of this hill. So we're going to go like this. Now, we have the 3 dotted lines. Now we're going to put the line segments on. So the first line segment is where the reactants are. And now what we're going to put is line segment 1. Circle number 1, which is line segment 1. And that's just the PE, or potential energy, of the reactants. PE of reactants. And that equals 60 kilojoules. All right, that's line segment 1. Now, this next line segment, really important. It's from the reactants to the top. So this is line segment 2. Line segment 2. And remember, line segment 2 goes from the reactants to the top. That's where the molecules or the particles were coming toward each other with a lot of potential energy, and they smashed into each other. So line segment 2 broke the old bonds. And so line segment 2 is considered the activation energy. And the activation energy runs from 60 to 80. So the activation energy is 20 kilojoules. And for letter A, there's a bunch of stuff under activation energy that you have to know. For letter A, activation energy, like we talked about before, breaks the old bonds. Letter B, activation energy always runs from the reactants to the top of the reaction. So RxN is an abbreviation for reaction. So runs from the reactants to the top of the reaction. So that's activation energy. Remember, reactants to the top breaks old bonds. Okay? So that is line segment number 2. Line segment number 3 is this one. Now this is an interesting line segment because it goes all the way from the top of the graph all the way to the bottom. So this is called activated complex. An activated complex is 80 kilojoules. A underneath. Well, why in the world is it called activated complex? Well, remember my 2 molecules of HI? So remember, they have potential energy. They're rushing toward each other. That means they're going up the hill, up, 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 up. And finally, when they collide at the top, they form a complex, you know, like a complex of buildings for a college or a university. They form a complex right there. So they're crashing into each other right there. And what's happening, 2 things are happening at once. So for letter A underneath activated complex, so this is the biggest thing that's happening right there at the activated complex. Old bonds are broken and new bonds begin to form. Okay? And the other thing about activated complex, very easy to pick out that line segment because it runs from the top to the bottom. So, runs from the top to the bottom. Okay, that is line segment number 3. Now, line segment number 4 is probably one of the most important line segments on the whole graph. Line segment number 4 runs from the reactants and the products. It's between the reactants and the products, so we're going to go like this. And this is line segment number 4. Now, you have to understand something about this graph. We put 20 kilojoules of energy in to break the old bonds, okay? That's called activation energy. And we got out from 80 down to 20. We got out 60. But you got to remember something. You can't say, oh, that reaction gave off 60 kilojoules because you invested 20 kilojoules to break the old bonds right here. So you can't count 20 of the kilojoules in for making the total amount of energy. So the total amount of energy that was released here is from 60, the reactants, down to 20. So the total amount of energy released is 40 kilojoules. 40 kilojoules was given off because you can't measure that part since it took 20 to break the old bonds. All right? So for number 4, that line segment between the products and the reactants is called heat of reaction. It's how much heat was given off by the reaction. But the other term for heat of reaction, this is a biggie, is called delta H. And remember, the delta symbol, it means change in. H is heat, so delta H means change in heat. And it has a specific formula, very easy. Delta H always equals this. Products minus reactants. So in this particular graph, the products are 20, the reactants are 60. So the delta H of this reaction is negative 40. That's how much energy was really given off by this reaction. So it's negative 40 kilojoules. Negative 40 kilojoules. Now, watch. If we have a negative delta H, that means more energy was given off than added in. So whenever you see a negative delta H, that means it's an exothermic reaction. So a negative delta H is an exothermic reaction. And there's a lot more about that, but I just want to get all these done now. So I always do this with my class. This is the reactant, this is the product. If the products are lower than the reactant, that means more energy was given off, and it's an exothermic reaction. Okay, so the next line segment is line segment number 5. Line segment number 5 goes from the bottom to the products. And that just measures the PE of the products. And the PE of the products is 20 kilojoules. But where the products are located tells you everything you need to know about the reaction. So look at the products compared to the reactants. If the products are lower than the reactants, that means they're more stable. So for number 5, PE of the products is 20 kilojoules. Let's put down A underneath. So the lower the products are, the more stable they are, okay? And we're not going to write this down, but if the products are lower than the reactants, once again, that means more energy was given off than put in. So if the products are lower than the reactants, it's an exothermic reaction. So putting all that together, put down letter B. So if the products are lower than the reactants, this is what it means. That means that delta H is a negative and that the reaction is an exothermic reaction. And you can tell just by looking and seeing where the products are. The lower the products are, the more stable they are. Remember, this was the reactant, this was the product. How could I make the products more stable? I could have let it burn all the way down. And then that means the products would be way down here with potential energy, less potential energy, much more stable than the reactants. Okay, so I'm going to show you something. In New York State, we have this. Heats of reaction. And they give you all these reactions. And the one easy thing is, it gives you delta H on the right-hand side. And once, like we said before, if delta H is negative, that means that the reaction is an exothermic reaction and you got out more than you put in. And the bigger the number, the more energy given off. So for here, the biggest number is negative 10,943 kilojoules. And look what it is. C8H18, that's octane, which means it's gasoline. So when you burn gasoline, that means it gives off a tremendous amount of energy. And it's an exothermic, delta H is negative. Now, we're not going to go over, if it's positive, obviously that means you're putting in more than you get out, but that's going to be the next video. Okay, now, what we have to do now is this. We are going to go into factors that affect the rate of reaction. How can you make the reaction go faster? Well, here's how I explain it to my kids. I tell the kids, if they were all in like ninja jumpsuits, all black jumpsuits with, when they put on the mask, they can't see anything. And they have a Velcro strip right in the back of their back. And so all the tables and chairs and everything is out of the room, and all my 17 students are just walking around. Sometimes they bump into each other, but most of the time they don't make a proper collision, because if they bump in from front to front, nothing, front to back, nothing. They have to bump into each other back to back. And if it's not a hard bump, then they won't stick together. So what we're talking about is 17 particles in here walking around, and they have to have proper orientation and enough activation energy to make a bond. All right? So I asked my students, how could I make this reaction faster? I'm getting bored. There's not too many bondings going on. There's not too much reaction going on. So how could you do that? And they all, almost every single class goes, if we heat up the temperature. So I tell them, if I heat up the floor, you're going to run around more, you're going to collide into each other more frequently, and you're going to make the rate of reaction go up. So one of the first most important things to make the rate of a reaction get higher is increase the temperature. And then from there they go, well, how about increasing the pressure? Well, yeah, it will work. Increasing the pressure will work, but they have to be gas molecules, because pressure really doesn't affect solids or liquids. So I tell them, if I moved in the walls of our room, that would be like increasing the pressure, and if they were gas molecules, that would increase the rate of reaction. So we have increased the temperature, increased the pressure. The next one is a real good one. The next one is, think about it. If you put a sugar cube in a glass of tea, it does dissolve, but it takes a while. But if you take that sugar cube and you crush it up into granules and put it in that tea, it dissolves almost immediately. So what we're talking about is surface area. So if you increase the surface area of something, it's really going to react faster. And I always tell them, if you have a puddle of gasoline on your table and you light it, the gasoline will light on fire. But if you keep that puddle of gasoline on your table overnight, it all evaporates, and you walk into a room and light a match, the whole room would blow up because you have much more surface area. Same thing about making a fire. You just don't take a branch or a log and put a match underneath it. It won't work. You got to shave that branch or log into kindling, increase the surface area, and then you can light it on fire. So now we have several things: increased temperature, increased pressure, increased surface area. All right? The next one, My most favorite, remember, my students are walking around, they can't see anything, they have Velcro in the back, and I'm getting bored because they're not hitting each other. So I walk out of the room, I walk back in with a burlap sack, and I tell them, I've got something in the burlap sack. And then I drop it on the floor, they hear a thunk, and then they hear a rattling noise. And of course they freak out because it's about a 6-foot timber rattler. And so they all run around trying to get away from it, and they're all smashing into each other, and that increases the rate of collisions, more frequent collisions, so the rate of reaction goes up. Well, then after that, I take the snake, put it back in the burlap sack, and walk out. So that snake wasn't itself used in the reaction, it just made the reaction go faster. So that was called a catalyst. A catalyst speeds up the rate of reaction without being used in the reaction. Now, look at this reaction on the board. How could I make this reaction go faster? Well, it took 20 kilojoules of activation energy to break the old bonds. If I put a catalyst in there, that would knock down the activation energy, so it would look like this. That's what a catalyst does. Now, a catalyst lowers the activation energy so the reaction goes faster. It didn't make any more energy because it didn't touch the delta H, but it did do two things. It changed two line segments. It cut down the activation energy, and it also cut down the activated complex. So when you put in a catalyst, it knocks the top down a little bit from the reaction, but it never ever changes the delta H. That stays the same. Okay, so now here's what we have for increasing the rate of a chemical reaction. Increase temperature, increase pressure if it's a gas, increase surface area, increase a catalyst, and then there's two more. The other one is I tell my students they're walking around, I open the door and I bring in another classroom. So I've increased the concentration of reactants. If I add more reactants, there's going to be more collisions. So now I have increased temp, increased pressure, increased surface area, increased concentration of reactants, and a catalyst. We got one more. Let's say these two molecules are going to collide and there's going to be a chemical reaction. Right? These two. That's methane and CO2. Then I have these two, HI and HI. They're going to collide and make a chemical reaction. So my question to my students would be, which reaction would actually go faster? And obviously, the first thing you have to do in order to have a chemical reaction after you have a proper collision and enough activation energy is to break the old bonds. So how much energy would it take to break 2 bonds compared to how much energy would it take to break 8? So the less bonds you have, the quicker the rate of reaction. So the final thing that increases the rate of chemical reactions would be the nature of the reactants. If the reactants have a lot of bonds, it's going to be a slower rate of reaction. Okay? All right. So this was an exothermic reaction. So the next video we're going to talk about is going to be the opposite. And if you know an exothermic reaction means you got more energy out than put in, well, then an endothermic reaction means you got to put in more energy than you got out. So that will be our next video.